In this video, we're going to discuss Dijkstra's algorithm, which solves the single source shortest path problem for directed or undirected weighted graphs. It is important to note that Dijkstra's algorithm is not suitable for graphs containing negative edge weights, and we will discuss in more detail why this is the case in a later video, but to give a brief explanation, it is because Dijkstra's algorithm is a greedy algorithm, and that means it makes global decisions based on local information. And if we want to solve the single source shortest path problem for graphs containing negative edge weights, we will have to use a different algorithm, which is the Bellman-Ford algorithm, and we will discuss this later on as well. For the purposes of this video, we're just going to run through Dijkstra's algorithm shown by the pseudocode here, and we're going to do this by considering an example. So we want to perform Dijkstra's algorithm on this undirected weighted graph shown here. But before doing so, we need to consider some initial conditions required to perform Dijkstra's algorithm in the first place. Firstly, we need a keys array, which stores the key values or priorities associated with each vertex. And in this case, for Dijkstra's algorithm, the priority will be the shortest path from our source vertex to the vertex at the index we are considering. And initially, all these values are set to infinity. So we're going to set our key array, all the values, to infinity. And by the end of Dijkstra's algorithm, this will store the shortest path from our source vertex to the vertex at the index we are considering. So for example, if we want to find the shortest path from our source vertex to vertex 2, we would look at what is under our index of 2, and this value, after Dijkstra's algorithm has executed, will show our shortest path from this source vertex to vertex 2. And we're also required to build a heap with these key values, and more specifically a min heap. And this is because we want the minimum path from our source vertex to every other vertex. And to keep things simple, we're going to consider this array, this keys array, as our heap, and we can just visually see what is our minimum value as the algorithm progresses. So this is going to keep things simple when we're running through the algorithm, as you'll see in a little while. And finally, we're going to have our parent array, which we have discussed in many other algorithms that we have previously gone through. So now we have all the initial conditions out of the way, and we can start to perform Dijkstra's algorithm. And you can see that we have one parameter, which is s, and this represents our source vertex. And our source vertex, for the purposes of this example, we're going to make as 0. So looking at our first line of our algorithm, we have this change operation which changes s to 0 in our heap. So s being our source vertex of 0, we're going to change this to 0. And note that this change operation is going to trigger heapify and rearrange our heap in order of minimum to maximum. But please remember, to keep things simple, we're going to consider this key array as our heap, and we can visualize what is our next smallest element by just looking at our array. So now we fall into this while loop, where this while loop will terminate when our heap is empty. So we first pop off or dequeue from our heap our next smallest element. So our smallest element, by looking at our key array, is going to be 0, because every other value is infinity. So we're going to pop off 0 now. And this is our first iteration of the while loop. So let's write to the side 1, representing our first iteration. And we're going to have this variable u, which represents our value that we dequeued from our heap. And this is our vertex 0 in this case. Now we fall into this for each loop where we check every adjacent vertex of u, or in other words, we want to check every neighbor of u, which is our vertex 0. So the neighbors of our vertex 0 are 2 and 4 in this case. So we can just write that in here. So we have 2 and 4. And now before manipulating our parent array and our heap, we need to satisfy this if condition. And this if condition states that v has to be in the heap. So let's consider our neighbor v being 2 for this case. So we need to check, is 2 still in the heap? Or yes, it hasn't been popped off, right? So 2 is still in the heap, and we need to make sure that this inequality holds. So let's write to the side here, 2, and we want to see if this inequality holds. So key of u, remember u is 0, and the key value of u is 0, plus w of uv, and this means the edge weight from u to v, and remember u is 0 and v is 2, being the neighbor we are considering, and the edge weight from 0 to 2 by looking at our graph is 4. And this must be smaller than key of v, and our key of v is our neighbor 2, so our key value at 2 is infinity. And so we need to check if this inequality holds, and is 4 smaller than infinity? Yes, it is. And so we can fall into this if statement and update our parent array and our heap. So in our parent array, we want to chuck u where our v index is. So u is 0, and this is going to be the parent of our index 2. So 0 is our parent of 2. And we also update our heap with this key of u plus our weight of u to v, which is what we calculated up here, which is 0 plus 4, which is 4. So at v, which is 2, this is going to be replaced with 4 instead of infinity. And now we can repeat this for our next neighbor, which is 4. And is 4 still in the heap? Yes, it is, right? Because it hasn't been popped off yet. And we need to check if this inequality holds. So key of u, which is 0, right? And plus our edge weight from u to v, which is our edge weight from 0 to 4. And 0 to 4 is 8 in this case. And we want to check if this is smaller than our key value of v, and v is 4 in this case. So looking at our key array at 4, we have infinity again. And so is 8 smaller than infinity? Yes, it is. So we can update the parent, and the parent at 4 is going to be 0. And we also update our key array, and our key array is going to have the value 8 in it, right, from this calculation here, which we already calculated in our if statement. And that concludes our first iteration of the while loop. So now we continue to our second iteration, and we dequeue our next smallest element, right? And our next smallest element, by just looking at our key array, is going to be 4. So we pop off our vertex 2. And so that means that u is going to be 2. And now we can find our neighbors. So we can just follow as before. Our neighbors of 2 are going to be 0, 3, and 4. And I should note that you can perform these operations in any order, but I'm just going to go from smallest to highest to keep things in a nice order. So now we can just go into this if statement and check, starting with 0. Is 0 in the queue? Well, no, it's not, because we've already popped it off. So we don't go into this if statement, and we can stop right there. So 0 is not considered now. And now we can consider 3. So is 3 in the queue or the heap? Well, yes, it is. It hasn't been dequeued yet. So we can go into making this calculation. And the calculation is key at u, which is at 2, and that's 4, plus our edge weight from u to v, which is our edge weight from 2 to 3, and 2 to 3 is 10. We want to check if this is smaller than our key value of v, and that's our key value of 3, and key of 3 is infinity. So is 4 plus 10 or 14 smaller than infinity? Yes, it is. So then we can update our parent array at 3, which is going to be 2. 2 is a parent of 3, and our key value is going to have key of u plus uv, which is this calculation here, 4 plus 10, which is 14. And now we can do a similar thing for 4, where is 4 still in the heap? Well, yes, it hasn't been DQ'd yet. And now we can write out our calculation again. So key of u, which was 4, right? Our key of 2, plus our edge weight from 2 to 4, right? 2 to 4 is going to be 2 by just looking at the graph. And we want to check if this is smaller than our key value at v, and v is 4. So our key value at 4 is 8. And is 4 plus 2 6 smaller than 8? Well, yes, 6 is smaller than 8, so we can update our parent array. So at 4, now it's no longer 0, it's going to be 2. And now we can update our key value. Instead of 8, it's going to be 4 plus 2, which is 6. So that concludes our second iteration of our while loop, and now let's continue. So our third iteration, we are going to DQ again, and that's going to be the next smallest element, and our next smallest element is going to be our vertex 4, which has a key value of 6. So that means that u is going to equal 6, and now we can go into this for each loop and check the neighbors. So the neighbors of, well, this shouldn't be 6, this should be 4, our vertex 4, which has a key value of 6. So our vertex 4 has our neighbors 0, 2, and 1. So let's write that in order, 0, 1, and 2. And we can check all these values one by one in this if statement. So first considering 0, is 0 still in the heap? Well, no, it's been popped off, so we can ignore that. Is 1 still in the heap? Well, yes, it is. So we can consider doing the inequality calculation for that. And that is key of u, key of 4 is 6, plus our edge weight from 4 to 1. 4 to 1 is 1 by just looking at the graph. We want to check if this is smaller than the key value at v, which is the key value at 1, and that's infinity. So obviously 7 is smaller than infinity, and so we can update. And this key value is going to become 6 plus 1, 7, and we got to update the parent at 1, which is going to be our u value, 4. And now we can check 2. So is 2 still in the heap? Well, no, it's just been DQ'd previously, so we can stop there. And that ends our third iteration of our while loop. And now moving on to our next iteration, 4. We are going to DQ our next smallest element, and we have 7 and 14 to consider. So 7 is obviously our smallest priority, and so we're going to DQ our vertex 1, and that means u is going to be 1. And then we can check the neighbors again. So v, our neighbors of u, are going to be the neighbors of 1, which are just 3 and 4. And we got to check, is 3 still in the heap? Well, yes it is, because it hasn't been DQ'd yet. So we can try the inequality calculation and see if anything needs to be updated. And so the key at u, which is the key at 1, and that's 7, plus the edge weight from u to v, which is the edge weight from 1 to 3, and 1, 3 is 4. And we want to check if this is smaller than our key value at v, which is our key value at 3, and that's 14. And 7 plus 4 is 11, and 11 is smaller than 14, so we are going to have to update our parent and our key, or our heap. So instead of 14, we're going to have 11, and this is going to correspondingly change our parent. Instead of our parent of 3 being 2, we're going to have our parent being 1. And now we can consider 4. So is 4 still in the heap? No, it has already been DQ'd, and so we can stop there. And now finally we can do one more iteration. So let's do 5 here of our while loop, and we DQ our last element. There's only one more element left, which is 3. And so u is going to equal 3, and that means our neighbors of 3 are going to be 2 and 1. So let's just write that in order, 1, 2. And then we fall into our if statement again, but remember that we need to check if 1 and 2, our neighbors, are in our heap, and everything's been dequeued, so we will never get into this if statement. And so we terminate there. And then going into our while loop one more time, you can see that this while loop will end when our heap is empty, and you can see there are no more elements in our heap as everything has been dequeued, and so we terminate Dijkstra's algorithm. So that is our walkthrough of Dijkstra's algorithm, and you can see we end up with this key array of our shortest path from our source vertex, which was 0 in this example, to every other vertex. And we also have our parent array, which keeps track of the parents of each vertex. And we should just fill in this last value here, which is 0, and this is going to be undefined. Because remember, the parent of our first vertex, there is no parent, so we can just leave that as undefined. So now let's leave some room to analyze our results. Here we're going to analyze our results from Dijkstra's algorithm by considering our two resulting arrays. So starting with our parent array, we're going to be considering our first vertex, which is 0. And this is connected to our vertex 2, as 0 is the parent of 2. And then the parent of the children of 2 is going to be 4. Right, because 2 is the parent of 4. And then we can find the child of 4 being 1, as 4 is the parent of 1. And finally, the child of 1 is going to be 3, as 1 is the parent of 3. And now we can fill in our key values, our priorities, which contain our shortest path from our source vertex. And remember, our source vertex for this example is 0, which we chose arbitrarily. So our shortest path from our source vertex to 0 is 0, because trivially the shortest path from our starting vertex to our starting vertex is going to be 0. And let's find our shortest path from our starting vertex 0 to 2. So that's going to be looking at our index 2, which is 4. So this distance here is going to be 4. The shortest path from 0 to 2 is 4. And now let's find the shortest path from our starting vertex 0 to 4, which is going to be looking at our index 4, which is 6. So we've already gone 4. We can add 2 here from 2 to 4 to get to 6. And then we want to find the shortest path from 0 to 1. By looking at our index 1, our key value was 7. So we got 4, 5, 6, add 1 more to get to 7. So the shortest path from 0 to 1 is 7. And finally, to find the shortest path from our starting vertex 0 to 3 is found by looking at our index of 3, which is 11. So we've already got 4, 5, 6, 7. So we have to add 4 more to get to 11. So the edge between 1 and 3 is going to be 4. And we can show this path on our example. So we go from 0 to 2, which is 4, and then we go from 2 to 4, which is 2, and then 4 to 1, which is 1, and then 1 to 3, which is 4. So that's going to conclude this video on the introduction to Dijkstra's algorithm, and in the next video we're going to analyze the complexity of this algorithm.